Okay, ladies and gentlemen, class recording for Tuesday, September 20th has begun. All right? Yesterday, we reviewed the video that you guys watched on Friday, and it talked about the introduction to mechanics. And we said we're doing mechanics, we're studying what? Motion. Okay? And Alexa, do you want to answer the next one, or do you want somebody else to take over? Maybe I should ask you the question, then it'd be good. So, when we are studying motion, there are 4 things that we want to know about that motion in order to describe it. Do you want to take this, or do you want somebody else?
I'll take it.
Okay, go ahead.
Where is the object?
Where is the object?
What is the object doing now?
What is it doing now?
What will the object be doing in the future?
What's it going to do next?
And when are all these things occurring?
And when are all these things occurring? And if we can answer those 4 questions, right, we do a good job of describing that motion. Right? So these are our W questions, right? Where, what next, and when. There's one W question that's missing out of this, right? Who, right? It's the object. But what's the other W question that's missing there? Why? Why is the question that we get into next unit when we start talking about forces, okay? So right now we're just describing. All we're doing is telling you what's going on, what's happening next, okay, all those things. We'll get into why in the next unit, okay? So, we started with where, and we talked about distance and displacement yesterday. To reinforce those concepts, I would like you to look at the sheet that I gave you today, and there is a picture of these 2 students walking through this hallway, okay? And there are 2 separate problems. One says quick example 2.2, and then there's this one that says practice problem number 2. I'd like you to do practice problem number 2 because you guys are a little bit behind the other class, so I want to try and get us caught up today, okay? So instead of doing both of those problems, we'll just do practice problem number 2. So let's take about a minute and talk to the person next to you, and let's answer those 2 questions that are involved with practice problem number 2. Ready? Go. What does it say? Where are they starting from? 30 seconds. There's 2 parts to that question. Make sure you answer both parts. Yeah. All right, let's discuss. First, like I said, you guys are a little bit behind, so let me ask you this question. Did we get those 2 answers? Yes. Okay. Do we understand how we got the 2 answers? Yes. Okay. Does anybody not know how I got those 2 answers? And don't be a chicken, raise your hand, okay, if you don't know, okay? All right, so let's discuss. Gotcha. Okay, go ahead, Sophia. Okay. That's a sig dig thing, so I just wanted to make sure sig digs were going with that, okay? So based on our calculations there. All right, so Jenny, are we good? Sorry, I didn't mean to call you out of the video like that, but okay. Do you want me to go over a little bit or no? Do you want me to go over where these came from, or are you okay? Are you sure? Okay, all right. Because I mean, if we have if we need to go over it, let's go over it, but there's some other things that I want to try and get to, okay? So I'm being 100% serious. If you don't understand, raise your hand and we'll go over it, okay? It's good for everybody to review. Okay, we're good so far? All right, the negative part's okay with everybody too, and okay? All right. So we said that distance and displacement talk about where an object is in terms of motion, right? During a motion, how far did it go, where did it end up versus where did it start? Good there, okay? So that answers the first question, the where. So let's spend some time talking about the second question, what? Now, before we get into the details here dealing with what, yesterday I mentioned to you guys that the beginning part of physics, especially establishing these concepts, is a lot of vocabulary. And we need to understand our vocabulary. It's going to be very apparent here in the next part when we deal with what is the object doing now, because we're going to introduce two new concepts, and they're two words that you know and you've used before, and you have used them interchangeably, but they're not the same. So we need to make sure we keep them straight. Okay? So with that warning, let's get into the next thing. So, describing what the object is doing now. We'll start off and talk about speed. Speed is defined at the rate at which distance is traveled. The rate at which distance is traveled. Or a ratio of the distance an object moves and the time it takes to move that distance. So before we go any further, let's talk about the first bullet point, the rate at which distance is traveled. Whenever we describe something as a rate, we are comparing it to something else. And what is that something else that we are comparing it to? Whenever we describe something as a rate, there's always one factor that's included in our comparison. Time, all right? So whenever rate shows up, all right, rate relates to time. Always, always, always. Okay, so we'll use that a little bit later on today as well when we do some more definition. Okay? So, speed we define as the ratio of the distance an object moves and the time it takes to move that distance. Mathematically, how do we represent ratios? Fractions, right? So speed is going to be a fraction. What's going to be in our fraction? Distance and time. Patrick, where does time always go when we're talking about a rate? On the bottom. So time's going to go here, and in this case, we're describing it, or we're relating it to distance. We're comparing it to the distance, okay? So speed is distance over time. Okay? The comparison of the distance over the time. Okay? Unit-wise, what are we going to measure? What do we measure distance in? Let's go more base unit. Meters, right? And then what do we measure time in? Seconds. So our unit for speed is meters over second, or usually we say that meters per second. Okay? Not yet. Okay, that's the next one. All right. Good with that definition so far. Okay? So let's do a pretty straightforward calculation. Here's a picture of a stick figure girl running a race. Okay? It's a girl. Can you see her little ponytail there? Right? I know that it's possible for guys to have ponytails, but in stick figure world, if you have a ponytail, you're a girl. So, all right. So if we want to calculate the speed of this runner, we need to know two things, right? What do we need to know if we're going to calculate the speed of the runner? Distance and time. So we know that speed is equal to distance over time. Okay? So we take a look here, and we have a ruler set up next to this track of the race, right? And it's giving us distances. And then there's some stopwatches to give us some times. Now, while the race goes all the way to the 100-meter line, right? The time only relates to a certain portion of this race, okay? Which portion of the race does that time relate to? Only 50 meters. So we're going to plug in 50 meters here, okay? Now, to review and to get some trickiness here, all right? Let's talk about measurements, okay? The certain place, according to this ruler, is which place of our measurement? The tens place is certain. And that means that our uncertain digit has to be what? Well, the place is, what place is uncertain? The ones place, right? Tens for sure, ones is uncertain, okay? So, if we were going, like if we were measuring a distance here, right? We would measure that distance as what? Like where the blue arrow is. What would be an acceptable measurement of that distance? 85. Okay? That would be a perfectly fine measurement. Okay? That's fine. At 85, right? Okay? Henry, 85 has how many significant digits? 2. Okay? And that means if we're going to use this ruler to measure something else, how many significant digits do our measurements have to have? 2. It appears that this girl is right on the 50-meter mark. But if we just write 50, how many significant digits is that? That's only 1. So how do we turn that measurement into 2 significant digits? Put a decimal point at the end of it. Jenny, is there anything after that decimal point? No, because if there was, that would turn it into 3 significant digits. So this 50 decimal point is a proper measurement of the distance with the correct number of significant digits. Okay? All right. Time-wise, how much time are we talking here? If you do it properly, we can skip the significant digits discussion. Jack, how much time are we talking about? How about 6.0 seconds? All right. According to this stopwatch, we know where the 1, the 2, the 3, and the 4 are, right? And that means the 1's place is certain, and we'd have to go 1 place past that. So here we'd have to go 6.0 seconds. Okay? So now you do a little math, and your calculator gives you, anybody got their calculator out so they can do this real quick? So, right? I think Sophia's going to beat you to it. Okay? So your calculator gives you what when you plug it in there? 8.3333333333, right? That's what your calculator will give you. Okay? But how many significant digits should our answer have? 2, because we're dividing 2 numbers that have 2 significant digits. So we should round our answer here to 8.3. Okay? No bar over the top, just 8.3. Okay? And then unit-wise, we just talked about that the unit for speed is meters per second. Okay? Good there? Jenny, go ahead. Well, in that case, we would sort of be extrapolating it out to the end of the race. According to the data that we have based on this distance and this time, that would be her speed only for this portion of that race. Okay? So let's keep it there for now. All right, good? Okay. Next, velocity. And here's what I said, right? Up until today, a lot of you probably use speed and velocity interchangeably. Okay? But they are not the same thing. So, average velocity, the rate of displacement of an object. Okay? Prizes, if we're talking about rates, what does that mean we got to include in our description? Time, right? So rate is still time. Okay? But now, what are we comparing that time, or what are we comparing to time? Or what are we looking at over time? Not speed. What does that definition say? What are we looking at over time? Displacement. All right? So velocity is a ratio between displacement and time. Okay? Whereas speed is a ratio of distance to time. Right? And we learned in the last section, those are two different things. Okay? So, velocity, a ratio between displacement of an object and the time it takes to complete that displacement. Like we said before, how do we represent ratios mathematically? Fractions. So, V equals, right? What's going on the bottom of this fraction? Time, because it's a rate. And that means what's going on the top of this fraction? Displacement. What notation are we using for displacement? Delta x, right? Or the change along the x-axis. Okay? Good there? So, units, right? What are we measuring displacement in? We still measure displacement in meters. What do we measure time in? Seconds. All right. So our unit for velocity is also meters per second. Fiona, go ahead.
And how would you know if there's some velocity or speed?
Let's get into that. In order to answer that question, let's look at the difference between distance and displacement. What's the big difference between distance and displacement? Because the number being positive or negative is telling us what? The direction. And that makes displacement what kind of a quantity? A vector quantity. The difference between speed and velocity is vector scalar. Velocity is a vector quantity. And we learned in the last section, if something is a vector quantity, what does it have to tell us? Two things it has to tell us. What does a vector quantity have to describe for us? Magnitude and direction. So in the case of velocity, the magnitude is telling us how fast that object is moving. But there also has to be a description of the direction of that movement. We discussed that for starters, we're going to limit our motions to one dimension. One dimension is a fancy way of saying what? A straight line. And Henry, that means for our direction, how many options do we have? Two. This way or that way. And how have we been distinguishing this way from that way?
Well, positive and negative.
Positive and negative. So velocities can be positive or they can be negative because they're not only telling you how fast something is going, but also which way it's going. Good with that? Let's apply it. Here's our lizard friend again, from the first page of your outline, and the two trips that we examined on the first page of the outline. And if I remember correctly, I believe his first trip, we figured out his displacement was positive 61 centimeters. Does that sound familiar? Yeah. Flip it to the first page of your outline and check it out. Is that positive 61 centimeters? And his second trip, we figured out that his displacement was negative 64 centimeters. Was that the right? Okay. All right. Good with that. Good with those two? Okay. We need those two things if we're going to be calculating average velocities. What else do we need to know if we want to calculate the average velocity of his trips? Time. So our stopwatches are back up there, right? So Jenny, can you tell how long his first trip took? Good. So this one took 4.0 seconds. And then his second trip, this first one here starts at 6. You see it starts at 6? Remember, he's going backwards in that one, right?
Oh.
It's 3 seconds, right? It's not negative 3 seconds because time doesn't have direction. Good there. All right. Henry, you got your phone out? You want to calculate for us? Or can you do this in your head? Okay. So Henry's gonna run some numbers for us, and he's gonna calculate our average velocities of each trip.
Oh, so the first one you see is 15.25, it's centimeters a second.
Okay.
And then, well, I mean with
Good. Okay. So 15 centimeters per second.
and the second.
But also, one thing that we should include on this, because it's a velocity, what does velocity have to tell us? Direction. So really our answer probably should be what?
Centimeters a second.
No, that's a unit.
Positive.
There we go. Okay. Did you do the second one yet?
Mm-hmm.
All right, what'd you get?
Negative 41.3333.
Okay. Which we'll round to,
Looks like 21.
not 21,
Negative.
negative 21 centimeters per second. Good with those two? Okay. Question. Which trip is faster, red or blue? Blue. Why? What does the negative sign tell us in negative 21? The positive and negative sign is only telling us what? The direction. It doesn't tell us anything about how fast. Negative 21 is faster than positive 15. It's just faster which way? Backwards, or the other way.
So just count the absolute value.
The so it depends on what we're talking about. Speed tells us what?
Distance traveled. And time.
Okay, the ratio between distance traveled and time. In everyday person words, speed is telling us what? Not like physics definition. Speed tells you what about an object? How fast you're going. What does velocity tell you? How fast you're going in a certain direction. So if we take the absolute value of velocity, what are we left with? We're left with the speed. Because speed doesn't make, so it depends on what you want to know. If I'm saying, what's the velocity of this lizard, you can't just tell me, or what's the fastest velocity, you can't just tell me 21, it's got to be negative 21. Because if I want velocity, I want how fast and which way. Does that make sense? Okay. So absolute value, taking the negative signs or the positive sign off of velocity leaves you with speed. Okay? But depending on what we want to know, sometimes that's okay and sometimes it's not. Does that make sense? Okay? If you have a question, are you okay? Okay. Good there? Okay. The last question that we want to answer. Oh, we already did this one. All right. The last question that we want to answer. What will the object be doing in the future? The when, we've been using when, right? It's a time. Okay. So let me do the definition right now, and then we'll do the application of it tomorrow at the beginning of class. What will the object do in the future? We refer to that as, oh, crud. Don't look, everybody. Okay. We refer to that as acceleration. Now, my warning goes out to you again. Make sure we know our vocab. Acceleration is a term that you've heard before. and it's one you've used. But here it means something specific. And it's described as the rate at which velocity changes. Rises, if it's a rate, what does that mean? It's over time. So we still got this part. What else do we need to know to calculate the acceleration of an object? Based on this description of acceleration. Not the velocity, what does it say? Does it say velocity? No. What does it say? The change in velocity. How are we going to represent the change in velocity? What notation do we use to represent the change in something? You answered the question before. Delta V, because it's the change in velocity. So, we represent rates as fractions. Acceleration is a fraction. What's on the bottom of that fraction? Because it's a rate. Time. And then what has to go on the top of that fraction? Delta V, the change in the velocity. Good there? All right. We'll pick it up from there tomorrow. We'll finish up the acceleration definition part, and then we'll start gathering some data for your lab that you're going to work on tomorrow and Thursday. Don't forget that homework on Google Classroom. You have a couple days to work on it. It's not, let's relate, what we're doing the next couple days. There is no homework, but work on it for the next couple days.